Said to forget you, so I get alone in my bedroom. I hold up the mirror against you. I fight up with ways to regret you. Now I just wanna give and let go. It's hard enough to feel the outgrow. I wish
All right. So I left off on monitoring sockets with netstat. Netstat's not a thing anymore. So we got this translation table between netstat stuff and SS. It looks like you can pretty much just give it most of the same flags. Just give it to SS. It's part of the IP Route 2 suite and is faster and more detailed because it reads kernel state directly instead of scraping proc like that netstat program did. I did TAP, which is TCP all ports. I don't really remember what TAP was, but if we do man SS dash T was threads, no, lowercase t. TCP dash A was all and dash P was processes. So SS TAP TCP all processes, and I think I have to do dash TAP. It used to be netstat, you didn't have to do the dash. Okay, if we do a man or a S trace on SS, so it's doing a lot of what's a bunch of writing. If I clear that, I want to do S trace, and then do dash C. So it does a lot of read links for the file descriptors, opening stuff, get directory entities. Yeah, a bunch of IO. But it said that SS doesn't scrape proc, but it certainly looks like it is doing that. Like if I drop to C and grep for proc here, slash proc maybe, and we need to send, sorry, it to 2 and 1, grep for proc. Yeah, it is reading from proc, so I don't know why it said that it's reading directly from the kernel. It's doing a lot of proc stuff here. So ChatGPT is lying. But I guess the vibe that I'm getting is that most of the commands are equivalent. You just replace netstat with SS, and maybe there's some differences. Okay, the netstat program displays the state of the internet and Unix domain sockets on a system. It is a useful debugging tool in writing socket applications. Most Unix implementations provide a version of netstat, although there are some variations in the syntax of its command line arguments across implementations. By default, when executed with no command line options, netstat displays information for connected sockets in both Unix and internet domains. We can use a number of command line options to change the information displayed. Some of these options are listed in table 61.1. If we just do SS, it gives us a bunch of stuff. And it's almost like, oops, it's this huge table of crap. Pipe that into less. Okay. So I'm guessing these are like some type of Unix domain socket, maybe? Not sure. Let's go back over to here. Okay. Okay. Here's an abridged example of the output that we see when we use netstat to list all of the internet domain sockets on the system. So if I do ss all inet, it does the same thing. Okay, so these are inet. It doesn't seem like inet to me. We man ss and look for dash dash inet. There's inet sockopt, which is just for socket options. So inet itself is not an option. But you can do TCP, UDP, v4, v6, BPF, shows socket classic BPF filters, DCCP, raw sockets, Unix domain sockets. Is dash A imply all these? Oops. Display both listening and non-listening. For TCP, this means establish connected sockets. Okay. Unix. So if I do ss-x, so these are all the Unix domain sockets. So I was right. These are Unix domain sockets. If I do -t, okay. For each internet domain socket, we see the following information. Proto, this is the socket protocol, for example, TCP or UDP. If I go back over to here, does not say proto. Even if I do U, there it goes, net ID. And if I drop A, there's basically no connections active. Maybe if I bring up a browser, go to google.com. This should generate some network traffic here and some persistent connections. There we go. So you can see it's coming from Chromium. We kill it. They're gone. Receive queue, send queue is the number of bytes in the socket receive buffer that are as yet unread by the local application. For UDP sockets, this field counts not just data, but also bytes and UDP header and other metadata. Send queue, this number of bytes queued for transmission in the socket send buffer. As with receive queue field, for UDP sockets, this field indicates bytes and UDP headers and other metadata. Local address is the address to which the socket is bound, expressed in the form host IP address port. By default, both components of the address are displayed as names. Unless the numeric values can't be resolved to corresponding host and service names, an asterisk in the host port of the address means the wildcard IP address. Forward address is the address of the peer socket to which the socket is bound. String */* indicates no peer address. State is the current state of the socket. For a TCP socket, a state is one of those described in section 6136. I don't see state here. Oh yeah, here, established. That's what that means, established. So if you go back to looking at Unix, which I think was X, so these are established. Then uster, this is Unix streaming versus Unix datagram. That's what that is. Cool. For further details, see netstat main page, various links and specific files. In the directory prod net allow the program to read much of the same information that's displayed by netstat. These files are named TCP, UDP, TCP6, UDP6, and Unix. With the obvious purpose is for further details, see the proc manual page. Using TCP dump to monitor TCP traffic. TCP dump program is a useful debugging tool that allows the super user to monitor the internet traffic of a live network, generating a real-time textual equivalent of diagrams such as figure 61.3. Where was that at? 61.3. Oh, okay, interesting. Despite its name, TCP dump can be used to display traffic for all kinds of network packets, e.g. TCP segments, UDP diagrams, and ICMP packets. For each network packet, TCP dump displays information such as timestamps, the source and destination IP address, and further protocol-specific details. It is possible to select the packets to be monitored by protocol type, source, and destination IP address, import number, and a range of other criteria. Full details are provided by the TCP dump manual page. The Wireshark, formerly Ethereal, Wireshark.org program. I remember when it used to be called Ethereal because I'm old. Program performs a similar task to TCP dump, but displays traffic information in a graphical interface. For each TCP segment, TCP dump displays a line of the following form: source, destination flags, data sequence number, acknowledge, window, urgent, options. These fields have the following meaning. I think it's pretty obvious what they mean. Maybe the flag section. This field contains 0 or more of the following letters, each of which corresponds to one of the TCP control bits described in section 6161. SYN, FIN, PSH, reset, ECE, and CWR. Data sequence number. This is the range of the sequence number space covered by the bytes of the packet. By default, sequence number range is displayed relative to the first byte monitor for this direction of the data stream. The TCP dump -S option causes sequence numbers to be displayed in absolute format. ACK, this is a string of the form ACK_num, indicating the sequence number of the next byte expected from the other direction. This connection window is a string of the form WIN_num, indicating a number of bytes received buffer space available for transmission in the opposite direction of this connection. Urgent. This is the string form of urg_num, indicating that the segment contains urgent data that is specified at the specified offset within the segment. Options. The string displays any TCP options contained in the segment. The source destination flags fields always appear. The remaining fields are displayed only if appropriate. The shell session below shows how TCP dump can be used to monitor the traffic between a client running on a host Pukaki and a server running on Takebu. In this shell session, we use 2 TCP dump options that make the output less verbose. The -T option suppresses the display of timestamp information. The -N option causes host names to be displayed without a qualifying domain name. Therefore, for brevity, and because we don't describe the details of TCP options, we have removed the options field from the lines of TCP dump output. Server operates on port 55555. So a TCP dump command selects traffic for that port. The output shows the 3 segments exchanged during the connection establishment. So say, hey, sudo TCP dump -tn port so and so. Oops. I always do that. Alright, advanced topics, TCP dump. Alright, we are here. These three segments are the SYN, SYNAC, and ACK segments exchanged for the three-way handshake. The following output: the client sends the server two messages containing 16 and 32 bytes respectively, and the server responds in each case with a 4-byte message. For each of the data segments, we see ACK sent in the opposite direction. Lastly, we show the segments exchanged during the connection termination. First, the client closes its end of the connection, then the server closes the other end. The above output shows the 4 segments exchanged during the connection termination. Socket options. Socket options affect various features of the operation of a socket. In this book, we describe just a couple of many socket options that are available. An extensive discussion covering most standard socket options is provided in Stevens et al. 2004. See the TCP UDP IP socket and Unix man pages for additional Linux specific details. The set sock opt and get sock opt system calls set and retrieve socket options. So we used this before in our Unix domain socket credential programs. Set sock opt. Yeah, this. Wait a minute. That is not what I would have. Oh no, it's get sock opt. Excuse me. Sorry. All right. For both set sock opt and get sock opt, sock fd is a file descriptor referring to a socket. The level argument specifies the protocol level to which a socket option applies. For example, IP or TCP. For most of the socket options that we describe in this book, level is set to sole socket, which indicates that the option that applies at the socket's API level. The op name argument identifies the option whose value we wish to set or retrieve. The op val argument is pointed to the buffer used to specify or return the option value. This argument is pointed to an integer or structure depending on the option. The op length argument specifies the size in bytes of the buffer pointed to by the op val. For set sock opt, this argument is passed by value. For get sock opt, op length is a value result argument. Before the call, we initialize it to the size of the buffer pointed to by op val. Upon return, it is set to the number of bytes actually written to that buffer. As detailed in section 6111, the socket file descriptor returned by a call to accept inherits the values of settable socket options for the listening socket. Socket options are associated with an open file description. This means that a file descriptor duplicated by the consequence of dupe or similar or fork share the same set of socket options. A simple example of a socket option is SO type, which can be used to find out the type of the socket as follows. So you just say int op val, then we just declare some memory here for some stuff, and then we say op len is equal to the size of the val, and then we're going to write into the val, and here's the length. I'm curious why that's a pointer. Why is that a pointer to a socket length type? Is that const pointer? Let's do man gets, I think it's to get sock opt. So yeah, it's a pointer. I guess it's where it's gonna write the length, which I'm fine with, but then why do we assign the length here if we're gonna write into it? Doesn't really make sense. After this call, op val contains the socket type, for example, sock stream or sock dgram. Using this call can be useful in a program that inherited a socket file descriptor across an exec, for example, a program exec by inetd, since that program may not know which type of socket it inherited. SO type is an example of a read-only socket option. It is not possible to use set sock opt to change the socket's type. Yeah, because it's established when it's created. All right, so now we're getting into some of the options here that might be interesting. So the SO reuse adder socket option serves a number of purposes. See Chapter 7 for details. We concern ourselves with only one common use to avoid the error adder in use, address already in use, error when a TCP server is restarted and tries to bind a socket to a port that currently has an associated TCP. There are two scenarios in which this occurs. This usually occurs. A previous invocation of the server that was connected to a client performed an active close, either by calling close or by crashing, e.g. it was killed by a signal. This leaves a TCP endpoint that remains in the time wait state until the 2MSL timeout expires. A previous invocation of the server created a child process to handle a connection to the client. Later, the server terminated while the child continues to serve the client and thus maintain a TCP endpoint using the server's well-known port. In both these scenarios, the outstanding TCP endpoint is unable to accept new connections. Nevertheless, in both cases, by default, most TCP implementations prevent a new listening socket from being bound to the server's well-known port. The error adder in use error doesn't usually occur with clients since they typically use an ephemeral port that won't be one of those ports currently in the time wait state. However, if a client binds to a specific port number, then it can also encounter this error. To understand the operation of the SO reuse adder socket option it can help to return to our earlier telephone analogy for stream sockets. Like a telephone call, we ignore the notion of conference calls. A TCP socket connection is identifiable by the combination of the pair of connected endpoints. The operation of accept is analogous to a task performed by a telephone operator in an internal company switchboard. When an external telephone call arrives, the operator transfers it to some internal telephone within the organization. From an outside perspective, there is no way of identifying that internal telephone. When multiple external calls are being handled by the switchboard, the only way of distinguishing them is via the combination of the external caller's number and the switchboard number. The latter is necessary when we consider that there will be multiple company switchboards with the telephone network as a whole. Analogously, each time we accept a socket connection on a listening socket, a new socket is created. All these sockets are associated with the same local address as the listening socket. The only way of distinguishing them is via the connections to different pure sockets. In other words, a connected TCP socket is identifiable by a 4-tuple, i.e. a combination of 4 values of the following form: local IP address, local port 4, and IP address 4 port, and the protocol, because you can have UDP and TCP. But he did state up here, a connected TCP socket, yeah. Okay, the TCP specification requires that each such tuple be unique, that is, only one corresponding connection incarnation can exist. The problem is that most implementations, including Linux, enforce a stricter constraint. A local port can't be reused, i.e. specified in the call to bind, if any TCP connection incarnation with a matching local port exists on the host. This rule is enforced even when the TCP could not accept new connections, as in the scenario described at the start of this section. Enabling the SO reuse adder socket relaxes this constraint, bringing it closer to the TCP requirement. By default, this option has the value 0, meaning that it's disabled. When we enable the option by giving it a non-zero value before binding a socket, as shown in listing 61.4, setting the SO reuse adder option means that we can bind a socket to a local port even if another TCP is bound to the same port in either the scenarios described as we start this section. Most TCP servers should enable this option. We have already seen some examples of the use of this option in listings 59.6 and 59.9. I just want to find a Go server. Do I have a Go server in here? I have sendfile.go. Does that actually do a listen though? Yeah, it does a listen. So if we make and then we do strace and build send file. And then we're going to send 2 to 1 and grep for, what is it? Reuse adder. Yeah. So they're setting it on their socket when they listen. Makes sense. Cool. Inheritance of flag. Oops, sorry, I'm on the wrong page here. Yeah, inheritance of flags. I want to TA. $61. All right. Inheritance of flags and option across accept. Various flags and settings can be associated with an open file descriptions and the file descriptors. Furthermore, as described in section 61.9, various options can be set for a socket. If these flags and options are set on a listening socket, are they inherited by the new socket created by accept? We describe the details here. On Linux, the following attributes are not inherited by a new file descriptor returned by accept. The status flag associated with an open file description. The flag that can be altered using the fcntl setfl operation. These include flags such as non-block and async. The file descriptor flags, which is close on exec, pretty much. fcntl set own, set sig, file descriptor attribute acts associated with signal driven IO. On the other hand, the new descriptor returned by accept inherits a copy of most of the socket options that can be set using set secopt. Subset 3 is silent on the details described here, and the inheritance rules for the new connected socket returned by accept vary across Unix implementations. Most notably, on some Unix implementations, if open file status flags such as non-block and async are set on a listening socket, then they are inherited by the new socket returned by accept. For portability, it may be necessary to explicitly reset these attributes on a socket returned by accept. Boop. So basically, maybe check the docs. TCP versus UDP. Given that TCP provides reliable delivery of data while UDP does not, an obvious question is, why use UDP at all? The answer to this question is covered at some length in chapter 22. Here we summarize some of the points that may lead us to choose UDP over TCP. A UDP server can receive and reply to datagrams from multiple clients without needing to create and terminate a connection for each client. A transmission of single messages using UDP has a lower overhead than is required when using TCP. For simple request-response communications, UDP can be faster than TCP, since it doesn't require connection establishment and termination. Appendix A of Stevens 96 notes that in best case scenario, the time using TCP is 2 times RTT plus SPT. So that's round trip time. In this formula, round trip time is RTT is round trip time, the time required to send a request and receive a response, and SPT is time spent by the server processing the request. On a wide area network, the SPT value may be small compared to the RTT. For UDP, the best case scenario for a single request response communication is RTT plus SPT. This is 1 RTT less than the time required for TCP. Since RTT between hosts separated by a large or i.e. intercontinental distances many intervening routers is typically several tenths of a second. This difference can make UDP attractive for some types of request response communication. DNS is a good example of an application that uses UDP for this reason. Using UDP allows name lookup to be performed by transmitting a single packet in each direction between servers. UDP sockets permit broadcasting and multicasting. Broadcasting allows the sender to transmit a datagram to the same destination port on all of the hosts connected to a network. Multicasting is similar, but allows the datagram to be sent to a specified set of hosts. For further details, see Chapter 21 and 22 of Stevens et al. Certain types of applications, e.g. streaming video and audio transmission, can function acceptably without the reliability provided by TCP. On the other hand, the delay that may occur after TCP tries to recover from a lost segment may result in transmission delays that are unacceptably long. A delay in streaming media transmission may be worse than a brief loss of the transmission stream. Therefore, such applications may prefer UDP and adopt application-specific recovery strategies to deal with occasional packet loss. An application that uses UDP but nevertheless requires reliability must implement reliability features itself. Usually this requires least sequence numbers, acknowledgements, retransmission of lost packets, and duplicate detection. Example of how to do this shown in Stevens et al. 2004. However, if more advanced features such as flow control and congestion control are also required, then it's possibly best to use TCP instead. Try to implement all these features on top of UDP is complex. And even when well implemented, the result is unlikely to perform better than TCP advanced features. So an example of a protocol that went down the route of building reliability on top of UDP is Quick, I think it was called. Sorry, wrong one. This guy. QUIC. Yeah. Replace TCP and accelerate web traffic, operating over user data protocol, which provides built-in transport layer security, TLS encryption, reduced latency via faster handshakes, and improved connection resilience during network changes, such as moving from Wi-Fi to cellular. Unix and Internet domain sockets have many other features that we have not detailed in this book. We summarize a few of these features in this section. For full details, see Stevens et al. 2004. Out-of-band data. Boop, boop, boo. Out-of-band data is a feature of stream sockets that... Is my stream on YouTube up right now? Let's see. Yeah. Okay. Out-of-band data is a feature of stream sockets that allows a sender to mark transmitted data as high priority. That is, a receiver can obtain notification of the availability of an out-of-band data without needing to read all of the intervening data in the stream. This feature is used in programs such as Telnet, RLogin, and FTP to make it possible to abort previously transmitted commands. Out-of-band data is sent and received using the message OOB flag and calls to send and receive. When a socket receives notification of the availability of out-of-band data, the kernel generates the SIG USR signal for the socket owner. Normally, the process using the sockets and sets the FCNTL set own operation. When employed with TCP sockets, at most 1 byte of data may be marked as being out of band at any one time. If the sender transmits an additional byte out of band data before the receiver has processed the previous byte, then the indication for the earlier out of band byte is lost. TCP's limitation of out-of-band data to a single byte is an artifact of the mismatch between the generic out-of-band model of the socket's API and its specific implementation using TCP urgent mode. We touched on TCP urgent mode when looking at the format of TCP segments in section 6161. TCP indicates the presence of urgent out-of-band data by setting the urgent bit in the TCP header and setting the urgent pointer field to point to the urgent data. However, TCP has no way of indicating the length of the urgent data sequence, so the urgent data is considered to consist of a single byte. Further information about TCP urgent data can be found in the RFC so-and-so. Under some Unix implementations, out-of-band data is supported for Unix domain stream sockets. Linux doesn't support this. The use of out-of-band data is nowadays discouraged, and it may be I've never even heard of this stuff. It may be unreliable in some circumstances. An alternative is to maintain a pair of stream sockets for communication. One of these is used for normal communication while the other is used for high priority. Yeah, I mean, makes sense. An application can monitor both channels using one of the techniques described in Chapter 63. This approach allows multiple bytes of priority data to be transmitted. Furthermore, it can be employed with stream sockets in any communication domain, e.g. Unix domain sockets. Makes sense. The send message and receive message system calls. The send message and receive message system calls are the most general purpose of the socket I/O system calls. The send message system call can do everything that is done by write, send, and send to. The receive message system call can do everything that is done by read, receive, and receive from. In addition, these calls allow the following. You can perform scatter gather I/O, that's nice, as with read V and write V. When using the send message to perform gather output on a datagram socket, or write V on a connected datagram socket, a single datagram is generated. Conversely, receive message and read V can be used to perform scatter input on a datagram socket, dispersed with the bytes of a single datagram into multiple user space buffers. We can transmit messages containing domain-specific ancillary data, also known as control information. Ancillary data can be passed via both stream and datagram sockets. We describe some examples of ancillary data below. Linux 2633 adds a new system called receive message, which is receive M message. This system call is similar to receive message, but allows multiple datagrams to be received in a single system call. This reduces the system call overhead in applications that deal with high levels of network traffic. An analogous send M message system call is likely to be added in future kernel versions. Let's see if it's there. Man to send MMSG. Look at there. Send multiple messages on a socket. Okay. Passing file descriptors. Using send message and receive message, we can pass ancillary data containing a file descriptor from one process to another process on the same host via Unix domain socket. Any type of file descriptor can be passed in this manner. For example, one obtained from a call to open or pipe. Example that is more relevant to sockets that. Hold on a second. What is this? An example that is more relevant to sockets is that a master server could accept a client connection to a TCP listening socket and pass that descriptor to one of the members of a pool of a child server process, which would then respond to the client's request. Although this technique is commonly referred to as passing a file descriptor, what is really being passed between two processes that reference the same open file description. The file descriptor number employed in the receiving process would typically be different from the numbers employed in the sender. An example of passing file descriptors is provided by the files SCM writes send C and SCM writes receive C in the socket subdirectory in the source code distribution of this book. So that is where you want to send and receive file descriptors. You send them as ancillary data. And you're really setting as a reference to a file description, not a file descriptor itself. Receiving sender credentials. Another example of the use of ancillary data is for receiving sender credentials via a Unix domain socket. These credentials consist of the user ID, the group ID, and process ID of the sending process. The sender may specify its user and group IDs as a corresponding real, effective, or saved set IDs. This allows the receiving process to authenticate the sender on the same host. For further details, see the socket and Unix man pages. Unlike passing file descriptors, passing sender credentials is not specified in SUSV 3. Aside from Linux, this feature is implemented in some of the modern BSDs, where the credential structure contains somewhat more information than on Linux, but is available on a few other Unix implementations. The details of credential passing on FreeBSD are described in Stevens et al. 2004. On Linux, a privileged process can fake the user ID, group ID, and process ID that are passed as credentials if it has, respectively, the capset UID, capset GID, and capset capsysadmin capabilities. An example of passing credentials is provided by so-and-so. So I did an example which didn't require the ancillary data. So let's pull up his example. Let's go to man7.org, and then this is the file. What file did he say it was? SCM cred receive. Source code. Here it is, online source code. SCM cred receive. Here we go. He uses get opt. What? No. Okay, we don't want that. See, he calls set sock opt here. All you have to do though with the Unix domain sockets, from what I could tell, get sock opt vim chapter 57 auth server.c. I think this is all you have to do here, is call get sock opt and write it into this credentials struct, ucred struct. So this rcred thing. This is like way harder than what it actually is. I think the way he's doing it is kind of dated. Okay. Moving on to sequence packet sockets. Sequence packet sockets combine features of both stream and datagram sockets. Like stream sockets, sequence packet sockets are connection oriented. Connections are established in the same way as for stream sockets using bind, listen, accept, and connect. Like datagram sockets, message boundaries are preserved. A read from a sequence pack socket returns exactly one message as written by the peer. If the message is longer than the buffer supplied by the caller, the excess bytes are discarded. Like stream sockets, and unlike datagram sockets, communication via sequence packet sockets is reliable. Messages are delivered to the peer application error-free, in order, and unduplicated, and they are guaranteed to arrive assuming that there is not a system or application crash or a network outage. A sequence packet socket is created by calling socket with a type argument specified as sock sequence packet. Historically, Linux, like most Unix implementations, did not support sequence packet sockets in either the Unix or Internet domains. However, starting with kernel 2.6.4, Linux supports socket sequence packet for Unix domain sockets. In the Internet domain, the UDP and TCP protocols do not support the sequence packet, but the SCTP protocol described in the next section does. Never use SCTP. We don't show an example of the use of sequence packet sockets in this book, but other than the preservation of message boundaries, their use is very similar to stream sockets. Okay, what is stream control transmission protocol? Okay. I'm not familiar with that. All right, SCTP and DCCP are two newer transport layer protocols. They're likely to become increasingly common in the future. They were not. The Stream Controller Transmission Protocol was designed to support telephony signaling in particular, but is also general purpose, like TCP, SCTP, provides reliable bidirectional connection-oriented transport. Unlike TCP, SCTP preserves message boundaries. One of the distinctive features of SCTP is multi-stream support, which allows multiple logical data streams to be employed over a single connection. Kind of like HTTP2 has like a stream multiplexing over a single connection. SCTP is described in Stewart and Z 2001, Stevens et al. 2004, and in RFC's so-and-so. SCTP is available on Linux since kernel 2.6. Further information about this implementation can be found at so-and-so. Throughout the preceding chapters that describe the sockets API, we equated internet domain socket stream sockets with TCP. However, SCTP provides an alternative protocol for implementing stream sockets created using the following call: socket inet stream, but this time we got a protocol argument called IP proto SCTP. Starting in kernel 2.6.14, Linux supports a new datagram protocol, the Datagram Congestion Control Protocol, DCCP. Like TCP, DCCP provides congestion control, removing the need to implement congestion control at the application level to prevent a fast transmitter from overwhelming the network. We explain congestion control when describing TCP in section 58.6.3. However, unlike TCP, but like UDP, DCCP doesn't provide guarantees about reliable or in-order delivery, and thus allows applications that don't need these features to avoid the delays that they can occur. Information about DCCP can be found at so-and-so in RFCs. Okay, we are through the sockets. Just got this summary. In various circumstances, partial reads and writes can occur when performing I/O on a stream socket. We showed the implementation of two functions, readN and writeN, that can be used to ensure a complete buffer of data is read or written. The shutdown system call provides more precise control over the connection termination. Using shutdown, we can forcibly shut down either or both halves of a bidirectional communication stream, regardless of whether they are open, where there are other open file descriptors referring to the socket. Like read and write, receive and send can be used to perform I/O on a socket. But calls provide an extra argument, flags, that controls socket-specific I/O functionality. The send file system call allows us to efficiently copy contents of the file to a socket. Efficiency is gained because we don't need to copy the file data to and from user memory, as would be required with calls to read and write. The get sock name and get peer name system calls retrieve respectively the local address to which a socket is bound and the address of the peer to which that socket is connected. We considered some details of the operation of TCP, including TCP states and the TCP state transition diagram, and TCP connection establishment and the termination. As part of this discussion, we saw why the time wait state is an important part of TCP's reliability guarantee. Although this state can lead to the address already in use error when restarting a server, we later saw that the SO reuse adder socket option can be used to avoid this error, while nevertheless allowing the time wait state to serve its intended purpose. The netstat and TCP dump commands are useful tools for monitoring and debugging applications that use sockets. The get sock opt and set sock opt system calls retrieve and modify options affecting the operation of a socket. On Linux, when a new socket is created by accept, it does not inherit the listening socket's open file status flags, file descriptor flags, or file descriptor attributes related to signal-driven I/O. However, it does inherit the setting of socket options. We noted that SUSV3 is silent on these details, which vary across implementations. Although UDP doesn't provide the reliability guarantees of TCP, we saw that there are nevertheless reasons why UDP can be preferable for some applications. Finally, we outlined a few advanced features for socket programming that we don't describe in detail in this book. Cool. I'm going to skip over those exercises as I am wont to do because I did some programming earlier today on this. If you look under chapter 61 here, we wrote an send file test program in Go. We did a send file between two files. Maybe we should change that to be mv send send between two files. Let's see. Make, clean, make. Yeah. So yeah, we sorry, my train of thought was interrupted there. So yeah, we did some test programs here for send file between. I should move this to be send file between two files. There we go. Okay, everything builds. And then we discovered errata as well. So I'll go commit that. Boop, 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 boop. Vim readme. We are done with sockets and almost done with this book. Get add readme. Get status. Get add chapter 61. Get status. We're going to say finish chapter 61. So that was my goal for tonight. I'm going to go ahead and hop off here. Tomorrow is Friday. And we have how many pages here left? 1400 minus 1288. So you got 112 pages left. So this is probably going to last into the weekend. I don't think I'm going to be able to get through all this tomorrow. So we have a chapter on terminals, which I'm like, I don't really know if I'm going to enjoy that. And then we have a chapter on alternative IO models, which includes epoll and select and all that stuff. And then we have a chapter on pseudo terminals, which he mentioned before in the book. Like terminals, I'm a little bit more familiar with than pseudo terminals, but yeah, terminals and pseudo terminals I'm not super excited for, but the alternative IO models I am. And then there's also a section, an appendice on tracing system calls, which is a couple pages that I think would be helpful, even though I use strace a lot already. I already read this. That was like a waste of time. Get opt was like annoying. I'll read this as well, and then this I might read. Kernel configuration. Cool. All right. I'm going to go ahead and hop off there. So tomorrow's goal is to get as much reading as I can done. Maybe I'll do terminals and pseudo terminals and then come back and just have chapter 63 alternative IO models be like the thing that I do over the weekend. Because I'd rather spend some time doing that, enjoying it, versus this terminal, pseudo terminal stuff. I'm not really like, I mean, I want to get like exposure to it, but I'm not really like wanting to dive into it deep. So yeah, I'll go ahead and push this up, and I will be on tomorrow after the gym in the morning. And hopefully we can get most of the terminal stuff done tomorrow. Cool.